Good morning, good afternoon, good evening. Intelligent agents and modern artificial intelligence in the world of responsible AI utilization. This is your professor T. Fareed Muhammad. This is a lecture series, the second lecture of PhD AI 830 at University of the Cumberlands at Kentucky. I welcome you to join me in learning this new and exciting era of the AI intelligent agent. Modern artificial intelligence has evolved from a niche academic discipline into a technology that shapes nearly every industry on the planet, from healthcare diagnostics to autonomous logistics. Before exploring how these systems work, it is essential to establish a clear framework for what we intend to understand the capabilities artificial intelligence brings to the table and boundaries it cannot cross. Everyone has a limitation, so has an artificial intelligence, and the ethical responsibilities that come without deploying it and with deploying it in the real world. Without this foundation, practitioners risk building powerful systems they cannot adequately govern or explain. The concept of an intelligent agent sits at the heart of modern AI design. An agent is any system that perceives its surroundings, processes that information, and takes purposeful action. A definition broad enough to include everything from a thermostat to a self-driving truck. That can be Tesla truck, by the way. Understanding what makes an agent intelligent and specifically what makes it act rationally is what separates ad hoc automation from genuine artificial intelligence. These distinctions matter enormously when organizations are deciding what to build, how to build it, and what guardrails to put in place. Contemporary AI systems have reached, and many domains are under its umbrella. So, if I rephrase it, in many domains surpassed human level performance across striking range of perceptual and generative tasks. Image recognition model can now identify tumors in medical scans with greater consistency than radiologists working under time pressure. It's not that radiologists are getting obsolete. Human in the loop counts. Speech recognition systems transcribe hours of audio in seconds with error rates that rival professional human transcriptionists. These achievements are not merely technical curiosities. They represent a fundamental shift in what tasks can be automated and at what scale. Natural language processing has unlocked an entirely new class of capability. Machines that can read, summarize, translate, and generate human text with coherence and nuance. Large language models are being used to draft legal contracts, write software code, and answer customer service queries in dozens of languages simultaneously, and synthesizes research literature that would take human analysts to process. That may take weeks to process. Star Trek is a good example that showed us such interpreter. The speed and scalability of these systems mean that tasks which are running or deployed by the AI deployment can run around the clock without food and anything. So before I go to modern AI capabilities, which I just discussed in quite detail, I would like to bring in the Amazon fulfillment centers deploy thousands of Kiva robots which satisfy every learning objectives in our current world simultaneously. They are designed with clear performance goals, packages moved per hour, operate under strict ethical and safety constraints, no collision, no worker injuries, function as intelligent agents perceiving shelf locations, deciding routes, acting on conveyors, make rational decisions under uncertainty, dynamic rerouting when an aisle is blocked, and run on architectures that have been refined through millions of hours of operational learning. Amazon engineers who built these systems had to master all six topics before a single robot moved a single box. And now let me jump into these capabilities which are mentioned on this slide, and I have elaborated in quite depth when you were looking at my slide at Amazon. I'll share with you another example. Siemens Healthineers has integrated AI image recognition into its medical imaging platforms, enabling radiologists to process CT and MRI scans significantly faster and with fewer diagnostic errors. Their AI models flag anomalies, measure organ dimensions, and prioritize urgent case automatically, a capability that becomes critical in hospitals processing hundreds of scans per day. Simultaneously, Siemens used AI-driven predictive models on its manufacturing lines to forecast equipment failures before they occur, translating raw sensor data into maintenance schedules that reduce unplanned downtime by up to 30%. This single company illustrates how the five capabilities on the slide that I shared with you earlier: perception, speech, translation, generalization, generation, and prediction can all be active within one industrial ecosystem. Despite its impressive headline achievements, AI remains deeply constrained in the ways that are often underestimated by organizations rushing to adopt it. The most fundamental limitation is that current AI systems do not understand anything in the way humans do. They detect statistical patterns in training data and reproduce those patterns when prompted. This human intervention in terms of AI's learning means an AI that has never encountered a truly novel situation has no reliable way to reason its way through it. It will either force fit a familiar pattern or produce confident nonsense, a phenomenon researchers call hallucination. In 2019, engineers at Knight Capital Group successor firms, and several algorithmic trading shops discovered that AI-driven trading models trained on pre-2008 market conditions behaved erratically when market volatility patterns shifted. The models lacked the common sense circuit breaker that a human trader applies instinctively. Something unusual is happening. I should stop and check, and instead amplified their positions based on patterns that no longer held. This illustrates all five limitations at once. The systems had no emotional or contextual awareness, were prisoners of their historical training data, made compounding mistakes without self-correction, could not apply the intuitive judgment a seasoned trader would, and critically lacked any human oversight mechanism that could intervene in the real time. Ethical AI is not a soft or optional concern. It is an engineering requirement with measurable real-world consequences. Fairness, privacy, accountability, transparency, and human level being are not abstract ideas or even ideals. They are properties that must be designed into AI systems from the earlier stage of development because retrofitting them after deployment is expensive, incomplete, and often too late. Regulatory bodies worldwide, including the EU's AI Act and the US AI Risk Management Framework, are increasingly treating these properties as legal obligations rather than aspirational guidelines. Bias is one of the most insidious ethical failures in AI because it often hides inside what looks like objective, data driven decision making when the dataset reflects historical human prejudice, whether in hiring, lending, policing, or medical treatment. An AI trained on the data will learn to reproduce and even amplify that prejudice at scale. The machine's outputs carry an air of mathematical authority that can make discriminatory outcomes harder to challenge than those made by a human decision maker who can at least be questioned and held accountable. In 2014, Amazon built an AI recruiting tool designed to screen engineer job applications automatically. The system was trained on a decade of historical hiring data that overwhelmingly reflected the company's male dominated workforce. Within 2 years, the tool had learned to systematically downgrade resumes that included the word women's, as in Women's Chess Club, and to favor language patterns statistically associated with male applicants. So Amazon shut the project down in 2018, but the case became a defining cautionary tale for the industry. Biased training data produced a biased model. The model made discriminatory decisions at scale, and the lack of transparency in the model's reasoning allowed the problem to persist undetected for years. It violated 4 of the 5 ethical principles on the slide that I shared with you previously. After AI safety, or even before AI safety, it is a discipline concerned with ensuring that AI systems behave reliably, predictably, and within acceptable limits, even as they operate in complex, unpredictable environments. Reliable performance means that a system must not only work correctly in controlled test conditions, but must maintain its behavior when inputs fall outside the training distribution, which in industrial deployments happens constantly. A safety failure in a software application may crash a program. A safety failure in an autonomous vehicle, a surgical robot, or a power grid management AI can cost lives. In aviation, Airbus integrates AI into its flight and envelope protection system on the A380 and A350 series. These systems continuously monitor hundreds of flight parameters and override pilot inputs that would push the aircraft outside safe operating limits, a form of real-time AI safety enforcement. However, following the lessons of the Boeing 737 MAX MCAS failure, the industry reached a clear consensus. No automated system should operate without transparent human oversight and reliable manual override. Modern Airbus safety AI is designed with explicit fail-safes, operator alert thresholds, and documented intervention protocols, illustrating all 4 safety principles on the slide. The system is reliable by design, hundreds against sensor spoofing, subject to continuous pilot monitoring, and embedded within a rigorous risk management framework certified by aviation regulators. An intelligent agent is the foundational conceptual unit of modern artificial intelligence, the theoretical building block from which everything from a spam filter to a self driving car is constructed. What makes an agent intelligent is not raw computing power, but the combination of four interacting capabilities: the ability to perceive the state of its environment, the ability to reason about what that state means, the ability to select an action in response, and the ability to execute that action in a way that moves it closer to a defined goal. The continuous cycle of perception, decision, and acting in terms of action is what distinguishes an intelligent agent from a simple rule following program. We have seen many people in our lives, and I'm pretty sure you also have seen as an individual the people who go by book, and then there are people with empathy and understanding and have the context with sympathetic thinking that change the world. By book means you're following to the period given in the book of a certain given guideline. It must expand with your human understanding. Where are we heading with the decision that we are about to take? Rio Tinto's AutoHaul system in Western Australia operates the world's largest fleet of autonomous freight trains, 240 locomotives hauling iron ore across 1700 kilometers of track without human drivers on board. Each locomotive is a fully realized intelligent agent. It perceives track conditions, signals, speed limits, and the positions of other trains through a network of sensors and GPS. It decides speed, braking profiles, and departure timing in real time. It acts by controlling throttle brakes and switches. So, in reality, controlling throttle as well as brakes and switches. And it pursues a clearly defined goal, delivering a specific tonnage of ore to the port within defined time and fuel efficiency. Windows AutoHaul has logged over 80 million kilometers of autonomous operation, making it one of the most operationally proven intelligent agents in heavy industry. A rational agent is one that at every decision point selects the action most likely to maximize its expected performance given everything it currently knows. The key word is expected. Rationality does not mean the agent always achieves the best possible outcome, because outcomes depend on factors the agents may not be able to observe or predict. Rationality means the agents make the best decisions available to its given knowledge, its capabilities, and the uncertainty inherent in its environment. This distinction matters because it sets realistic benchmarks for what we should demand of artificial intelligence. UPS or Orion on-road integrated optimization and navigation system is a masterclass in rational agent design and performance measure selection. The environment in which an agent operates is not merely a backdrop, it is a defining constraint that determines which architectures are viable, which algorithms are appropriate, and what level of performance is realistically achievable. A fully observable environment where the agent can see and complete, in terms of see the complete state of the world relevant to its decisions, permitting far simpler, and more reliable agent designs than a partially observable one, where the agent must maintain internal models and make inferences about hidden state. The difference between these two environment types can mean the difference between a rule based controller and a full probabilistic reasoning system. Oil and gas drilling operations represent one of the most challenging environment types in existence. Partially observable, sensors can measure pressure and temperature but cannot directly observe subsurface rock formations. Stochastic geological responses to drilling are probabilistic. Dynamic conditions change continuously as the drill bit descends, and continuous depth pressure and rotation speed are all real valued variables with no discrete steps. Baker Hughes has deployed AI drilling optimization systems marketed under the AutoTrack and iStar platforms. Now, that must cope with all four of these environmental challenges simultaneously. The five agent architectures on this slide form a hierarchy of increasing capability and complexity, and understanding when to use each of is one of the core competencies of an AI system designer. Simple reflex agents are appropriate only when environment is fully observable, deterministic, and required behavior can be captured by a manageable set of condition action rules. Again, manageable set that comes from the set membership. Set is a combination of entities bound to work with each other. There can be jointed sets, disjointed sets, there can be union sets, intersection sets, and subsets within the given domains. As soon as the environment becomes partially observable, meaning the agent cannot see everything it needs to make a good decision, a model-based approach becomes necessary because the agent must now maintain and update an internal representation of the parts of the world it cannot directly perceive. Goal-based agents add the capacity for deliverable in terms of deliberate planning. Rather than simply reacting to current state, they reason forward about how different sequences of actions will lead to or away from their defined objectives. Utility-based agents go further, replacing the binary question, does this action reach my goal, with a richer question, how much does this action improve my overall situation, permitting them to navigate trade-offs between competing objectives. Learning agents represent the apex of this hierarchy. Rather than relying on pre-programmed rules, models, or utility functions, they improve all of these through experience, adapting their behavior over time as they accumulate evidence about that works and what does not. Alphabet's Waymo autonomous vehicle platform is a near perfect illustration of all five architectures operating as layers within the single system, as we just discussed. The most important lesson from this lecture is that AI is neither magic nor a simple tool. It is a complex socio-technical system whose design requires simultaneous attention to capability, limitation, ethics, rationality, and architectural fit. An organization that deploys AI without understanding its limitations will be blindsided by its failures. One that ignores ethics and bias will build systems that cause harm at scale and face mounting regulatory and reputational consequences. And one that selects the wrong agent architecture for its environment will produce a system that is either dangerously oversimplified or unnecessarily complex and expensive to maintain. Intelligent agents that perceive, decided in terms of decision, and act in pursuit of goals are already the backbone of modern industrial operation. From warehouse robotics to financial trading to energy grid management, the rational agent framework gives practitioners a principled way to evaluate whether an AI system is actually doing what they intend it to do using performance measures that captures the full definition of success. The environment taxonomy helps engineers select the right tools before development begins rather than discovering the wrong fit after millions of dollars have been spent. Tesla's full self-driving system integrates every takeaways from this lecture into a single publicly deployed product. Its capabilities are extraordinary, processing 8 camera feeds, simultaneously detecting lane markings, reading traffic signals, and predicting the behavior of surrounding vehicles in real time. Its limitations are equally well documented. It struggles in heavy rain, novel road geometrics, and adversarial edge cases that fall outside its training distribution, which is why Tesla mandates that a human driver remains attentive at all times. Its ethical and safety frameworks are embedded in software update protocols, incident reporting pipelines, and regulatory engagements with NHTSA. It is a learning agent. Each vehicle in the fleet uploads anonymized driving data that improves the model for all the vehicles. Happy learning. See you in the third lecture.